Thanks everyone for being here. What is it? Okay, just press.
Got it. Yeah, we got it.
Okay,
Yes.
let's talk a little bit about Sean's science. Let's see, that's blocking the title. The title says that most of you know that Sean was a surfer, but I think he had a genuine interest in all different types of waves in the ocean. Can we get rid of that?
High floating medium control.
Yeah.
All right, great. Where is that? Hi.
Middle. No.
There you go.
Yeah.
Okay.
All right.
Sean liked waves, period, and that includes ocean internal waves. And when he came here as a postdoc, I think it was in 2016, maybe 2015, 15, yeah. I suggested a problem to him, which was to look at the question of whether big, strong ocean swell can generate significant internal waves. And the question was, might the coupling between surface and internal waves damp swell and therefore provide significant energy to the internal waves? And the conclusion of the paper that we wrote together is to the first question, no. And to the second question, perhaps. And I'll say, well, okay, before I talk a little bit about the history, no, I'll talk about the history first. Okay, full disclosure, when I came to Scripps as a postdoc in 1982, this problem was suggested to me by my advisor, Ken Watson. And I got about this far. I realized that internal waves at the ocean don't actually travel very quickly. 3.3 meters a second is a typical horizontal velocity. Actually, it's a maximum horizontal velocity. And swell is much faster. And so if you're looking for some kind of coupling between the swell and the internal waves, it's not going to happen in the situation that's sketched here, where I'm showing a packet of surface waves traveling at the top of the ocean, traveling along at, say, 10 meters a second. And the internal waves just stand no chance in keeping up with the ocean swell, if you want to think of it in those terms. And this is a famous picture originally due to Michael McIntyre, which shows what happens in an unstratified ocean with no internal waves. You get a packet of surface waves at the top, and it has this is the infamous deep return flow. As the surface wave packet travels, it pumps fluid down at the front, it travels around in a deep return flow and comes back up at the back of the packet, okay? And one of the things which we immediately discovered was if you made the ocean stratified, this problem is the deep return flow is completely different. It looks more like this, and this is radiation of an internal gravity wave by the packet, okay? But the message here is that if you're in two dimensions, if this is all that's happening in the XZ plane, this can't happen with realistic parameter values because the ocean internal waves are simply too slow to keep up with the wave packet, okay? There's very weak coupling in two dimensions. Wrong button? Okay. But of course, the problem isn't 2D, and this is where this is what I did with Sean. We looked at the full effect of 3 dimensions, allowing a packet. This is the location of the packet. It's quite small, the packet of surface gravity waves. And as it travels across the ocean, it leaves a pattern of internal waves behind it, which is a little bit like a Mach cone, if you're thinking of sound. And the point about that is, even if the internal wave crests are advancing at 3 meters a second, normal to the sides of the cone, the speed along the x-axis can be a lot greater than 3.2 meters per second. And that through that purely kinematic effect, you do get coupling in the 3D problem, which isn't present in 2D. And we did the math, and it's quite a mathematical paper, and Sean was wonderful at that. And the conclusion is basically the energy transfer is completely negligible for the effect on the surface gravity waves. But indeed, it might provide significant energy for a certain part of the internal wave spectrum, which is internal waves with frequencies close to the buoyancy frequency, which was the subject of Rob Pinkel's thesis when he was a student at Scripps. So I will stop there. Thank you, and fond memories of Sean.
I'll share again. And share again. How do we share? Zoom. Yeah, share the
Press
screen.
escape to bring the controls down.
And then I'm gonna hide this again.
Yeah, hide that.
Do we want to see?
It's
the
our
chat?
first symposium. We're still working.
I see a face missing. Oh, Nicole, are you monitoring that chat? Yeah. Okay. 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 Nope. Nope.
Okay, sorry.
Okay, so Sean came here and did a postdoc with Bill, and both his thesis work with Baylor and his postdoc with Bill was very theoretical work. And Sean had a real talent for thinking about theoretical work where you start with F equals ma, the Navier-Stokes equations, and you think about all the full complexity of what should happen in the ocean when you take all of those complicated terms and how they interact and put them together. And what we do as observationalists is watch what actually happens in the ocean and try to make sense of it. And so these are often sometimes different worlds where the theorists say, this is what the equations say should happen. And then we go out and we're like, huh. And can be a steep void in between those two spaces. And so one of the wonderful things about Sean was that he was able to sit in that in-between space and be an intersectional person and bridge some of the theoretical insights and observational work. And so after he did his postdoc with Bill, he approached our group and said he wanted to do try his hand at some observational work. And so we said we'd bring him to sea and he could try his hand at collecting some data and working with the data. And so one of the first things you do with someone who's new to going to sea is you give them, of course, the most dangerous job on a ship. Does anyone know what the most dangerous job? Greg.
It's to launch the XBT.
It's to launch the XBT. So people who have been through oceanographic hazing rituals at sea before know that the deployment of the XBT from the XBT tube requires an incredible amount of careful safety equipment and gear. Be careful, Sean. So here's Sean in his Ghostbusters style setup, courtesy in large part due to Greg, ready with all of his backpack and safety helmets to deploy the XBT. And so he came along with us on a number of cruises and decided to tackle some of the questions of things we observed that were the most confusing to us. And so does anyone know what is pictured here? Does anyone see? So this is, you can look out the window. Does anyone see all these slicks? Who knows what those slicks are? Anybody? Anybody? What's that? That's a good guess. They're not. They are internal waves. They are actually the surface signatures of internal waves propagating through. And one way you can tell they're internal waves is that compared to surface waves coming in, they move very slowly. And let's see if this works. This is a video by my friend and colleague Drew Lucas, who is here somewhere in the room. And you can see these slicks coming in. And you can see surface waves coming in fast, people going over across the bridge fast, and these waves are propagating in very slowly. So this is the surface signature of an internal gravity wave propagating in. And that's something we sort of think we understand. And we're like, yeah, you know, they come in, they're nonlinear, we sort of got it. But then here's a movie. This is the surface radar. So this is the fancy version of the previous thing where you could see on surface radar these things coming in. This movie was made largely by a couple of people, Alex Simpson and Kate Adams, who I think are both also here in the room. And you can see we had 3 research vessels going right around. You can see these things coming in. These are the surface signatures of internal waves coming in. But then one of them is not like the others. This one here that's labeled front stops propagating in. It slows down. It develops a whole bunch of wiggles and it falls apart. And so we often study two of the things that theorists put in different boxes are internal waves and fronts. And so what we had here was an example where one of them seemed to turn into the other. And so this was data gathered on a cruise that Sean was on, and he got fascinated by this stuff. And he sat there and we all were like, what is even happening here? These are two different phenomena. They have different physics. They have different parts of parameter space. They should not interact. And he went back and forth, looked at the data, looked at the theory, looked at the data, you know, scoured through decades worth of JFM papers that I could not understand myself, and found an explanation for what was happening here. And in a Freaky Friday sense, he found a certain part of parameter space where internal bores, if they get deep enough, they follow the same sorts of physical processes as a low mode very nonlinear internal wave can turn into a front, can turn into a gravity current. And he figured out the complicated theoretical approach that matched the observations. And there was an amazingly unique skill set, I thought, of him. In this paper, did I actually put the paper? Yeah, here was that came out after he passed away, was one of the papers that many of us who were on this paper was one of the papers I was proudest to be part of. And so that's it.
Thanks, Tim. Okay, so the last group will be a group of three friends of Sean, and the four of these guys shared all aspects of life together, of super enjoyment of all of this science and theory, adventure, and friends. And I'm gonna let them introduce themselves.
Hi, I'm Navid, and these are the Wagners.
We're not related.
No relation.
I'm Till Wagner.
I'm Greg Wagner.
Yeah, and yeah, we heard from Sean's family. We heard from Sean's mentors. We'll hear a bit more later. I just wanted to touch a little bit of what this gathering, what this event, what this symposium means for us, Sean's friends. And you know, yeah, we're three here, and I say Sean's friends, most probably half of us should be here, but it'll be a bit complicated, so like that, yeah. So Sean brought people together, and he's doing that now. I've seen people flying from all over the country to come here for this.
Navid came from Australia.
People flying from all over the world. I've seen people from Canada here. It's like, it's like me going back in time. I feel like I'm in Scripps, like in 2017, when, you know, Sean, I was office mates with Sean, and you know, all of these photos that you're seeing around were happening. So Sean was bringing people together and keeps bringing people together, and will keep bringing people together every year. And thank you, Sean, for that. Yeah, I don't even know what I'm reading. I mean, I could be talking here for hours, but I mean, it's an intense emotional situation for me. I felt pretty close to Sean. Like some people, a lot of people thought of us like almost like a couple. They would see me and say, "Oh, where's Sean?" Like they would see Sean, "Where's Navid?" I mean, all right. I mean, yeah, but I can see why they were like treating us like that. I mean, we were quite bonded, and yeah, there was a lot of goofiness, a lot of fun together with science, and we wanted to bring a little bit of Sean's spirit in the room, a little bit of the goofiness, a little bit of how we were all together having fun, and you know, it was how Sean would you know, bring the mood up. So we'll play a video. Perhaps this is the time. We have some technical difficulties here to overcome with the sound and the zoom and
back to live action. Here we have Till Wagner stroking into a beautiful insider, nice and steep, off the bottom, off the top combo, coming into the very inside section, looking for the air, but then pulls out. Raymond on the outside, nice cruisy right-hander, but then tries to do the air with his board only and succeeds. There are dolphins jumping. Oh, yeah. Check out the dolphins out the back. Judges giving him a 4.5 on that last wave for that aerial maneuver. One maneuver wave, pretty solid. Here we have our other contestants making breakfast. Looks like Navid is really taking charge, making a solid scramble.
Look at that wrist technique.
Very
up
progressive.
And over, up and over.
Very progressive. The judges are going to like that. We got Raymond Koo stroking out really hard on his knees, but Till Wagner perhaps more in position, but looks to the insider, and he's stroking for it. Looks like he's gonna make it. And here he goes.
Be a buzzer beater. He's up and
oh, he's up, and there goes the buzzer. Nice top turn. Wave slows down for him though. He's gonna ride it through all the way to the inside, milk it for the extra points. Raymond Koo up after the buzzer.
Mainsy, I think this is a victory lap for Ray. Are you about to take a ball?
Oh, but here goes Till on the insider. He knows that's the end. Right into the danger zone.
He claimed it also with the tongue out.
With the tongue claim.
There's a chance. There's a good chance.
You know,
here.
these judges have been very pro tongue claim. You know, but don't forget there, Ross, that the length of ride is a very important criteria for the judges. And Till Wagner with that last one had a very long ride, a little bit smaller wave, but he milked it all the way through the inside, through the danger zone, pulled out clean, tongue claim and all. So there's a chance as the judges tabulate their scores, we might see an upset.
We've got the first judge to score in.
Really?
They've been doing this for like 45 minutes. Oh, 2 scores in. What are they looking like, Ross?
We need a 5.67.
What was the highest
Oh, the
score
first judge
today?
is low. Second judge is also low.
Well, and that wraps it up for us today. Come back tomorrow for more live action when we have a little bit more swell, and our commissioner is expected to give the green light to the next heat.
Who wants coffee?
Great. Well, thank you for that wonderful introduction. And now it's my great pleasure to introduce our first speaker for this inaugural symposium in honor of Sean Haney. And that's Baylor Fox-Kemper, who's over here. He's a professor at Brown University, and he was Sean's PhD advisor. So Baylor studies small scale processes in the ocean, ranging from the submesoscale to sea ice. And Baylor was a great mentor to Sean, kind of in all the aspects that you need to be an academic. So research-wise, Baylor is at the forefront of the kind of research that's really changing things for us. And doing this kind of science that Sean really loved, and doing the part of science that's really difficult. So he takes that complex theory and actually puts it into the models that we're using to predict climate change. And so there are many examples of Baylor's wonderful research. The one that I'll pick out is he was the lead coordinating author of the oceans chapter of the most recent IPCC report. And the other part of Baylor that, you know, that he mentored Sean is how to live, you know. And I ran into Nick Pizzo an hour ago, and he was like, you know, we all love Baylor because he's a human. And I totally agree with you, Nick. You know, Baylor really taught Sean that a really important part of doing research is building a community. And you saw an example of, how Sean built his community at Scripps, with having surf sessions, going on adventures with friends. And a really important part of Baylor's building of community that Sean learned was to emphasize group karaoke. And so, Sean really became such a great scientist, I think, because of Baylor. So it's a great pleasure for me to introduce Baylor giving our inaugural talk. So, Baylor.
I just want to say that there's lots of seats up front. All the people in the back, there's lots of seats. There's
Yeah.
lots of seats. Come.
It'll take me a
Come
minute
sit.
to get things ready anyway, so come on in. And Nicole, people are hearing online. Yes, we think.
We are. It's good to see you guys.
All right, so thank you very much, Amy. I think you may have heard very much about it. I learned an enormous amount from Sean about how to build community. I think it's, when you work with a PhD student, it's like a 5-year relationship at least, and then continues on. And students take different approaches to what they're going to do. They come in with lots of skills, a few ideas. They get excited about new ideas that they're learning. And, some students will take all those skills and ideas and pack them to themselves like armor and then ram into the opposition. And then some people will, spread them out around them like seeds in a garden and let, big ideas grow. And Sean was the kind of person who treated ideas like friends. They were not only the things that he wanted to think about, but he used them to make more friends. So he linked up with his friends through ideas and brought together a bigger group that you've already seen on display today. So it was a great pleasure to work with him, a great honor. And sorry. So I was trying to think about how to start this lecture. And I was trying to think about, how to talk a little bit about Sean's science, as Jen and Bill also introduced pieces of it. And then I was thinking that would be looking backwards instead of looking forwards. And instead I came to the idea that I wanted to give a talk that Sean would have really liked. And that started to help focus things. And then at the end, I came to the idea that I wanted to give a talk that I would have liked to make with Sean. And so that's what I'm going to talk about today. So the title is Waves Affect and Detect Climate. And we've all heard, oops, I'm going to trip over this every time so we can watch. So Sean loved waves. Sean loved waves and banging into other things. That was the whole thing was, how do we put all these pieces together, these different pieces, and think about what they do? And so this work that Sean and I did was on the kind of small scales, but since then we've built that into a bigger picture, and it connects all the way to climate change. And so I'm going to try and get you all the way through that before the end of the hour. Oops, now I have to continue. So this is Sean, and whatever. He was at University of Colorado in Boulder with me until 2015. And so we'll talk about that. So this talk comes in 3 parts. The first one is waves affect ocean mixing and currents. And that was work that Sean was intimately related working. He was a big part of how we thought about that. There were a lot of different directions going at the same time. I'll give a little bit of a sense of that. And then another thing you can do with waves, which is related to the observational work that both Sean did, but that's ongoing here as well, is you can use waves to detect climate change. And there's something special about that. And then the air-sea group here, their challenges in measuring air-sea exchanges well enough to see climate in them, which is a slow trend underneath everything. Waves can help in that. I'm going to try and make that clear. And then finally, waves affect the mixed layer, a lot of the stuff that we talked about, and therefore climate. So I'm going to try and give you a little bit of recent work that I worked together with another bright young student named Galen Hall, where we're trying to quantify how much the mixed layer affects the climate system, or particularly changes in the mixed layer affect the climate system. So there are all kinds of waves. Surface water waves, we've already heard a little about. A lot of the processes leading to El Nino are also waves. Sound is a wave, phone calls are a wave, radio is a wave, epilepsy is a wave, traffic jams are waves. The aurora borealis is a wave. But we're going to focus on open ocean surface waves, surface gravity waves. And this is, I think this has to be a movie from Flip, because I don't understand how you could be so stationary and see a ship bouncing around like that nearby. But this is what open ocean waves look like. There's not so much breaking unless there's a lot of wind. There might be white capping, but it looks a little different than the waves out there at the beach. And you can see there are waves of all different lengths superimposed on top of each other. So we don't think of, it's not necessarily swell. It's not necessarily a simple pattern of waves. So one thing that waves can do is they can create turbulence, and the turbulence that's forced by waves, well, there's turbulence that happens when waves break, but there's a different kind of turbulence that's called Langmuir turbulence that's connected to waves. And Langmuir turbulence has a kind of classic signature. Sometimes I was hearing earlier that you can see them out here in slicks. This is a slightly more disturbing picture. This is after the Deepwater Horizon spill. That's oil, those streaks. And you can see down here, I actually have a pointer. Down here, there's an airplane for scale. The stripes like this, the glint off the waves, let you know that those streaks are perpendicular to the wave crest, and that's another signature of Langmuir turbulence. For the dynamicists in the room, there's a bunch of stuff you can look at and think about what all that tells you about Langmuir. But the only thing that I think is really important about this picture, other than the fact that this is oil collecting when Langmuir cells converge at the surface, is that we won't be able to resolve this in global climate models until about the year 2170. And that's given that computers are getting exponentially faster. These are small things and the world is really big. So the key agents that makes these Langmuir cells happen is something called Stokes drift. And so this is a nice little movie from Wikipedia that shows Stokes drift. So you're watching these little orbits. There's something called the orbital motion that goes up and down and kind of around in a circle underneath the waves. But it's faster at the top than it is at the bottom in this kind of wave. And so you don't quite make a circle. You come back and go a little bit farther each time in the direction of the wave propagation. That little bit of drift, cycle after cycle after cycle, if you average it over each cycle, that's the Stokes drift. And so now that I've explained that a little, you can see that it's decays with depth, goes in the direction of the propagation of the wave. And these are little particles throughout the fluid that are also tracking along with the Stokes drift. So you see it actually transports stuff. It's not just part of the wave propagation that travels through the medium without moving the medium. Waves in the open ocean can be very complicated. This is a nice example where this is a spectrum. So this is basically increasing frequency out from the center and different directions of the waves. Here's a big wind wave, you know, kind of broad-banded thing. And then there are two swells that are going in different directions. And so when you think about this Stokes drift, this is a nice monochromatic wave Stokes drift, but really you want a complicated set of waves. They're all pushing around stuff like this. And when you put that together, that's one of the motive forces for this Stokes drift, I mean, for this Langmuir turbulence. So how does Langmuir turbulence work? Well, if this is the direction of the wind and the waves coming like this, then there would be a Stokes drift that would be strongest at the top and then decay. And so it's kind of coming out of the board like this, strong at the top. And so if you imagine that there happen to just be some little anomalies, like little fronts or little jets or something that's happening on the surface, this little jet is spinning this way. This little jet is spinning this way. This little jet is spinning this way. This side of that jet is spinning that way. So there's actually vorticity in those little surface jets. And that Stokes drift shear is going to tip the vorticity over to the side. And when it does, it'll accumulate in these large helical overturning cells called Langmuir cells. And they align themselves in the wind direction. So their axis is in the wind and wave direction. And they converge at the surface. Why is that moving? Anyway, they converge at the surface and diverge at the bottom. And their convergences makes these long windrows, which is where the oil piles up at the surface convergences. And so that's the kind of mechanism of Langmuir turbulence. Once you have that mechanism in mind, we have a few ingredients. We've got turbulence, so 3D, non-hydrostatic kind of stuff. We've got this Stokes drift profile, and we've got an interaction, a set of interactions between the Stokes drift and the turbulence once you've averaged over the wave orbital velocities. So you can make simulations like these. These are, this one has only wind forcing at the surface, and this one has wind and waves. And let me restart it because it's a little clearer at the beginning than at the end. And you can see they differ in magnitude, and they also differ in direction. Like the streaks in this, this is vertical velocity. So this is stuff going up and down, like at the axis of those overturnings. They're going in a slightly different direction between here and there, and they have a different magnitude. So in essence, Langmuir turbulence is stronger, and it's oriented differently than wind-driven turbulence. And so it can mix more. And if you can mix more, you might make the upper ocean mixed layer, the upper ocean boundary layer, a little bit deeper. And that'll be important that we come back to later. And so this is one of the problems that John loved to think about. So we got it in our head that sometimes the waves would be going one direction and the wind might be going in a different direction because the waves had been either formed by wind far away or the wind had just changed direction. And if you examine the statistics of wave propagation and wind, the wind is sort of veering around and the waves keep going in a straight line. So it's a pretty common situation. And in fact, when we wanted to put this Langmuir extra mixing into a climate model, one of the things that we couldn't figure out was, what do we do with the case when they're not going in the same direction? Nobody had ever really thought about that. So it wasn't so hard to take one of those little models and make Langmuir turbulence under those conditions. But we realized pretty quickly that we needed to figure out what set the direction that the Langmuir cells went in. So this is now vertical velocity looking from above. The blue lines here are really the windrows, those convergence zones at the surface where the stuff comes together and collects. And these little arrows, I can tell you, each one of those arrows was a conversation between Luke Van Rokel, Sean, and I at a blackboard with the equations for Langmuir turbulence, trying to make a guess about which direction it would go. So you can see each day we had a different color of arrow. Most of them didn't work that well, but this dark green one actually ends up being a pretty decent direction. So once you have that, now you know the direction of Langmuir. Now you can use that because we can take the wave direction and the wind direction and project the strength of the waves and the winds in those directions onto this Langmuir direction. And when you do that, the dynamics of Langmuir cells arise just like they did in 1D. So through that work to figure out what the right theory was to predict the Langmuir direction and recognizing that we could project the winds and waves on, we took something that looked like this for different wave and wind directions. It just looked like a mess and made it something that looks like this, where almost all of the different directions collapse on top of one another. So then we knew what we were doing. We could predict the vertical velocity from the strength of the wind, the strength of the waves, the directions of the wind, and the directions of the waves. And the vertical velocity squared is the thing that mixes up the upper ocean. So we were off and running and could put it into climate models. Another problem that we were working on, I had worked on and we're working on around the time that Sean was in my group, were the submesoscale. So the submesoscale is bigger than Langmuir cell, so it's 10 kilometers or so. This is a picture of sea surface temperature. And these big eddies are mesoscale eddies, but these little wiggles along the fronts are submesoscale. And this is a nice picture in the Tasman Sea of false ocean color. So this is like, it's all blue and green in the real world, but they've made it pink and teal here so you can see the differences. But so different water types with different kinds of critters growing in them or whatever are colored here in different colors. And again, you can see big mesoscale eddies, but little submesoscale wiggles. And so the little submesoscale wiggles are classes of instability of fronts, essentially. And so a front is something that happens between colder water and warmer water at the surface, where there's a horizontal difference between the two. There's potential energy there because the warm water could go on top of the cold and the cold could go underneath. You need to extract some energy by lowering the center of mass of the fluid. So here's a front, and a front gets a long front current that comes from geostrophy, but then that along front current goes unstable. You start to get these little wiggles. And if you could see the numbers down here, the wiggles are kind of kilometer in scale. So that's a mixed layer instability. And Sean got really interested in what happens if do waves affect this scale as well, like just like they were strongly linked with the Langmuir scale, maybe they do. And there are actually two classes of turbulence. Well, there are many classes of turbulence that can arise in a front like this, but we were particularly interested in this one, mixed layer eddies, and then something else called symmetric instability that I'll show you a movie, what that looks like in a little bit. And we didn't realize it at the time, but this is from a later experiment, the so-called laser experiment. But convergence of submesoscales is a really important thing if you're interested in environmental consequences. I'm going to rerun this movie in a second. But just like with Langmuir cells, you can imagine that if stuff comes together at a front and went downward, you might collect things at the surface of a front. Turns out there is a secondary circulation that overturns at most fronts, the fronts that I like, the one that I just showed. We weren't paying much attention when we made those videos, but let me show you again what this is. So each of these is a surface drifter, like one of these guys. That's his little buoyant, kind of lifesaver ring at the top, and then a little sail. So they're about this tall, and they track the upper ocean water as it moves around. They've got a GPS in them. So this was an experiment where they put out a few hundred of these over about a 10-kilometer area. And now watch the pink ones. And this is kilometers in scale. So, they're spread out over about 15 kilometers. And they're going into some kind of magical submesoscale convergence zone. And they all go down the plug hole. So all the pink ones end up within 100 or 200 meters of each other, starting out at 10 kilometers. So if that was oil, you could go collect it all there after it had been nicely collected for you. Or if you were a critter trying to gather nutrients, that would be the hot spot. That's where they all would be. Or if you were a seagull and you wanted to go find the fish, that's probably also where they all would be. So these kind of things happen on these small scales. Maybe we should have known it in advance, because if you look at sea ice, it also is converging into the sea ice, into those frontal zones. And so you can see some mesoscale eddies here in the marginal ice zone, drawing in sea ice and bringing it together. Okay, so enough about that. Let's talk about bigger simulations, even bigger simulations. So this is a calculation. Oh, it's very jumpy. Sorry. It's not working very well. Well, I'll zoom in a second. So we decided, well, can we simulate those things at the same time? Can we simulate the submesoscales and the Langmuir cells at the same time? And these are so jumpy, but each of these is actually a movie of a little 1 kilometer by 1 kilometer box inside a 400 square kilometer model. And if you zoom in on one of those little ones, it looks like this. And so the color here is showing temperature. Where it is colored is showing vertical velocity. And so you see Langmuir cells, convergent zones, these little windrows all around, and then you see a big front in the middle. And we did this because we thought that the interaction between these was going to be interesting. Like in a second, you didn't even have to look for interaction. But you can see there's a lot of similarity. They're kind of zooming together, converging into each other. So that secondary circulation and the overturning of the little Langmuir cells is kind of mirrored, but just on different scales. So if we take that same front and just look at it in surface temperature, it looks like this. It's cold on one side and warm on the other. So it has that potential energy that I mentioned. You could extract energy. And I'll just note that the wind and wave direction is in the same direction as the front. If you look at the vertical velocity, you can see all the Langmuir convergences, and also that front looks like an awful lot like a Langmuir cell. If you put surface drifters into this flow, some of them go into Langmuir cells on the windrows, some of them drop into the front. And if you look from the side at that front, there is indeed a warm side of the front and a cold side of the front and an overturning circulation like this. And so here's the funny part. This is the thing that we didn't expect. If you take the same force that pushes the Langmuir cells down, it's part of that vortex tilting that I talked about, and you think about this thing and the vorticity of that larger front getting tilted over by the same mechanism, where does it go? It goes right there, right at that sharp point, right at the front of the front. So if the front aligns with waves, it gets sharpened, just like a Langmuir-Selle windrow does. And so it gets stronger still. But it only happens if the front is pointed in the same direction as the winds and waves for almost exactly the same reason that we had that wind and wave needed to be projected into the direction of the Langmuir-Selle. So it's the same mechanism occurring now in a submesoscale. And this isn't the Langmuir-Selles and the submesoscale talking to each other. It's actually the submesoscale talking directly to the surface waves. So surface waves are acting on larger features in much the same way. You can make a scaling for this. So this is something that, this is the kind of argument that Sean would have loved. This is a, what's the coefficient in front of this non-hydrostatic, this downward force right at the edge of that front, and it scales like something that goes with Stokes drift and the depth of the boundary, the depth of that current, the Stokes depth, and then an F times an L, so Coriolis and horizontal length scale. This looks sort of like a Rossby number, at least the F by L part. And so you can take, it's hard to estimate either of these independently, but if you take their ratio, it's very easy to estimate this in the real world. It just becomes the Stokes drift over the velocity times the depth of the boundary layer over the Stokes depth. And so here's a global map from a variety of observations and wave models. And you can see that those numbers are hanging out in here in the kind of 4 to 10 area, sometimes even bigger in the equator, sometimes lower. So we spend an awful lot of time thinking about when geostrophy is violated. We spend a lot of time talking about geostrophic fronts, and there's a small ageostrophic connection. And when you get into the submesoscale, this starts to be order 1, and you're like, now the fronts are totally different. They can converge because they're ageostrophic. This is the same thing. The other part of thermal wind, the hydrostatic balance is being violated by the downward force that's happening in the middle of those fronts. The ratio of these two being greater than 1 tells you that the non-hydrostatic effect comes in first and more strongly than the ageostrophic effect. So the interaction between waves and submesoscale fronts may be stronger than the ageostrophic effect in understanding how submesoscale fronts work. So Sean's first paper was interested in these kinds of instabilities. And so we were interested in so when a hurricane goes over, the mass of mixing, partially by Langmuir, partially by other stuff, and then that wake has to heal and needs to come through. So this little movie is showing, I started again. There's a mixed up hurricane wake, and then there's pulsing because there's a diurnal cycle and heating, and then there's some submesoscale eddies happening. So there's all kinds of stuff happening that are mixing, all kinds of stuff that's happening to re-stratify and to heal that scar left behind by the passage of a hurricane. Where Sean really took off from this was he was interested in whether not only the fronts, but the instabilities were affected by waves. So I want to talk about that, but I also want to talk about, you may notice that this has an awful lot of authors, this paper, Sean being the first one. That's everybody in my group at the time, plus my former supervisor. And so I had a crazy idea that we should get everybody in the group to collaborate on a paper. And so everybody did, kind of half an hour of work and came in with a random result. And then I was like, oh, now how do I make this all happen? This is just random, like brainstorming. How do we turn this into a paper? Anyway, Sean got totally fascinated by this and then went through and pulled everybody together, made all of the contributions fit together, synced them all up, and pulled this paper together out of that kind of crazy brainstorming. Some of these people are biologists, like it was a lot. And anyway, it just has a very nice paper with a nice conclusion about all of the observed hurricane wakes that we could get our hands on, and which of these processes we thought should dominate, just by doing the same kind of scaling arguments that I just showed for the epsilon versus Rossby. It's just each of these scales on different size, different depths, different widths, different rates of heating, different times of year, gives you a different scaling for each of these many things. And Sean brought all that together, figured out how to put all those together into a coherent story, and off we went. Okay, so do the waves actually interact with these bigger things? So we said that they're these guys, the mixed layer instabilities, and there are littler ones called symmetric instability. And at the time we kind of knew, well, I mean, we had like a simulation or two. So we kind of knew how they were, but we didn't know how big they were in the real world. So just recently, can we move this? I'll close that guy out actually. If I can read that, I think that's the button. In two recent papers, by Jihai Dong, who's another young scientist who started working with us, we figured out how to see how big those things are all around the world. So in the wintertime, the mixed layer eddies are kind of 20 kilometers ish near the equator, and then smaller 10 kilometers ish near the poles. In the summertime, they're much smaller, just a handful of kilometers near the poles, and maybe 10 kilometers or so near the equator. So if you convert this into the units of like, how long do we go before we can do this in the climate model without any kind of fiddling and any kind of theory? 2065, so still a little ways off. We can't just put these dynamics in, we still have to continue to understand them before we can put them in. And this other instability, symmetric instability, won't be globally resolved until 2090, because these are now 2 kilometers to 10 meters in scale. So smaller, still sub-mesoscale, still largely hydrostatic, still frontal related, but much, much smaller. And I would be happy to talk about the details of how we get at those, which is not easy, but I just want to say now we kind of know how big they are. Oops. And so do those things interact with waves? And so Sean, even before we had a map of how big these things were, figured out that actually the geostrophic, the mixed layer eddies don't interact strongly with waves because they're just kind of too big. But the symmetric instability does. And this is, sort of the coolest image out of all of that work is this one. So this is a little box and a symmetric instability. You can see it in the cross. So a front is going this way. In the cross frontal direction, there's velocity. So it's little structures that are kind of coming together like this from the sides. What do you got? What's happening?
We need those.
Oh, you need to open? That's fine.
Yeah.
No, it's good there. All right. It's okay. Thanks. Sorry. I keep closing it now. That's all I couldn't. Okay. All right. So this is just a little box. Here are some density surfaces. So we're sitting in a front like this. But if the waves are going one direction versus the front, they can make a front that should be symmetrically unstable, stable. So the missing stripes up here means that the symmetric instability is totally turned off by the waves. Or the other way around, you can make a region where there should have been no symmetric instability based on the normal parameters, go symmetrically unstable. So this is the figure that explains that waves at the top could either stabilize or destabilize the symmetric instabilities. And Sean did a series of nice calculations. This is one of the nicest ones. So this is a simulation, one of those turbulence simulations. On this side, we're seeing potential vorticity. So here's a front going that way, and then a front going this way, and another front going that way. This is the same over here, just looking at it in a different way. The Stokes drift here is coming out of the page. And the key agent here is the potential vorticity, including the effect of the Stokes drift. And so the blue here means the potential vorticity is negative, which means that it's potentially unstable to that symmetric instability. The red means positive, not unstable to symmetric instability, but unstable to Langmuir turbulence, then blue again. So now let me restart it so I can show you that guy again. Okay, so look at where the blues are. Look over here, and you're going to see red and blue stripes that go down really deep, all the way down to this layer. The base of the potential vorticity being 0 layer, see right there. Those are the symmetric instabilities, so they shouldn't be there were it not for the Stokes drift at the top. And then here, you're seeing Langmuir turbulence that's driven by the Stokes drift in a different way. So figuring out how to diagnose this, how to pull apart these different pieces, how to even see what these structures look like was all something that Sean just loved to think about. And so he figured out in the end a good way to do this was to follow the energy pathways, where the energy was going from the waves into the Langmuir instabilities, from the waves into the symmetric instabilities, and thereby be able to diagnose them. And even when they are even more muddy, this is a clean one where I can show you the phenomena, but we did a lot of other simulations where you couldn't see what was happening, but you could still use those diagnostics to tell what the pathways were from wave energy into the submesoscale. Okay. And then Bill talked about this already. So Sean had gotten the bug and he started banging waves into all kinds of things, banging them into internal waves, banging them different this kind of wave into front, all kinds of things. So in short, waves affect ocean mixing and currents, and Sean's work really helped us see a lot of those pathways. And even on the papers that he's not on, he was really like in the mix, shaking up our ideas, arguing with us, making us do better science. Okay, so now I'm going to go into these latter two pieces, which aren't stuff that I knew about at the time when Sean was in my group, but they are things that kind of build on this. And I want to, and we'll close on how waves affect climate. And it's through this ocean mixing that they really affect climate. So that's a warm up for the next part. So, okay, here's the IPCC. We talk a lot about climate change. This is the most famous climate change figure, or at least the update of it. This is called the hockey stick because it's flat and then it's got a blade of the hockey stick on it. This is the warming in degrees C since the pre-industrial on this axis. This is a reconstruction from paleoclimate, and this is the observed record over the 20th century. You have to move that guy. I'm just going to move it. I'm not going to turn it off.
Thank you.
So you can see which year we're talking about. So from 1850, which is industrialization started pretty much, to 2020, it's shooting upward. So you can say human influences or non-human influence, we don't know that yet, but the climate has warmed at a rate that's unprecedented in the last 2,000 years. That's what you mean. And here's the second most important figure in the IPCC. This is the human influence one. So this black line is the same as this black line. It's the observations of surface temperature. This tan envelope is all the models that include human and natural effects. And this teal envelope underneath is the same models, but not including human effects. And so if you think about that for a second, you can tell that we can tell the difference between with human and without human. And the observations only track in the with human. They've left the without human a long time ago, sometime in the 1950s. And they really separate out from each other sometime in the 70s or so. So we didn't have good enough measurements to do this in the past. And you really need the shape of the envelope, which gives you a sense of the uncertainty in El Nino when things are spreading these models apart. But now we can go to that sentence. So human influence has warmed the climate at a rate that's unprecedented in the last 2,000 years. And so, well, that's not a very oceanic story. What's the key part of ocean climate change? Well, ocean climate change often is talking about sea level rise, and sea level rise is really mostly the steric expansion, or the thermosteric and halosteric, if that wasn't covered up. The steric is when the ocean gets bigger because it gets less dense. And so if you heat it up, it gets bigger because it gets less dense. So this is a map of what all the models do under a very strong warming scenario up here and a weaker warming scenario here by the year. This is the change from 1995 to 2100. So you can see that sea level is rising in these kind of brownish regions. And where the slashes are is where the models don't agree. So that effect is about half of what the total sea level rise is, and it's about 0.5 meter in this upper one. And so if you live right here, like I do, you might be very concerned that that sea level rise is a lot. But the eddies are also playing a game here as well. There's variability in this, and the variability up and down to the sea surface height has everything to do with eddies. So the observations of the variance or the standard deviation of sea surface height has a pattern like this, seeing big currents that have big eddies. And here's what you get in a high resolution model. It looks sort of similar, but you get in a classic climate model doesn't have a good job, do a good job of representing that. And so sea level rise also has a hockey stick. So global mean sea level has risen faster since 1900 than over any prior century in the last 3,000 years. And this is the hockey stick. It maybe is a little bit wiggly as a hockey stick, but that jump is certainly different from everything going back. And those are numbers if you want to look at them, but the numbers are part of the story. So you can say, well, what are the mechanisms? What is submesoscales? What does Wagner have to do with this? Why am I going off on this diatribe about basics of climate change? Well, because when we take the energy, the excess energy that's coming in, that's being trapped on the earth, and figure out where it goes, most of it's going in the ocean. It's going in different layers of the ocean, like this, and then there's a little bit that's melting ice, a little bit on land, and a little bit of the atmosphere at the bottom. We can do exactly the same thing over here with the sea level budget and say, where's the sea level rise coming from? And most of it, or at least about half of it, is coming from expansion of the ocean. That thermospheric part I just talked about, part of it's from melting glaciers on land, part of it's from melting ice sheets on land. This part is increasing a lot. And then part of it's changing land water storage, which is taking basically ponds and rivers and putting them in the ocean. Okay. So, all right, what's the process by which you warm up the ocean? What's the process by which you change the salinity of the ocean? Well, you do it through air-sea fluxes, right? You know, you change the connection between the ocean and the atmosphere, between the ocean and solar radiation. And so you can take like the freshwater flux, that's precipitation minus evaporation, or the net heat flux, that's heat coming in and not going out, or the wind stress, which is putting energy or momentum into the ocean from the atmosphere. And then you can say, well, here's the observed trends. And then here is what the model changes over the whole of the century, essentially, that same difference. And then you say, does this look like that? You say, well, sort of. Does this look like that? Kind of. This, you know, like, that's a little worrying. And then the more worrying thing is, look at the stippling. The stippling here means that the observational change are not statistically significant, which is almost everywhere. This slicing means that the models are not agreeing with one another. We cannot collect the air-sea fluxes of any of the three carefully enough to constrain the models, and the models are in disagreement. And if the models are in disagreement about the freshwater flux, they're going to be in disagreement to some extent about the halosteric sea level rise. If they're in disagreement about this, they're going to be in disagreement about the thermosteric sea level rise. If they're in disagreement about this, they're going to be in disagreement about the currents, changes in the currents, and changes in the strength of the eddies. It's that variability of the sea level rise. So this is a worry. So how do we get around that? Well, one thing we can do is we can say, oh, let's take the energy, which is not the flux itself, it's the net accumulation of the flux. Even if we're not looking, we can't measure the changes in the flux. The ocean is paying attention. It's warming up or it's not. And so we can go just skip the flux altogether and just go measure the warming of the ocean. Or we could skip the freshwater flux and just go measure the changes in salinity in the ocean. What about the momentum part? How can we skip this and somehow get some sense of that? And that's where the waves come in. So we can observe the significant wave height, which is a consequence of the winds blowing the ocean, but it's not as messy as the winds. It's an accumulation of the winds. The ocean is watching even when we're not, and then we go see what the ocean has recorded about the winds that it's experienced. And so the significant wave height varies over a couple meters, you know, from 2 meters up to 5 meters or so around the globe. This is how off wave models are when driven with climate model winds. But you can see that's not so bad. It's smaller than this. So we can start talking about that, but we better have a measurement that's better than the bias. Here's the error, which is, you know, models disagreeing as well as in this one, kind of same order of magnitude as the bias. And then here's the inconsistency among different observations of the waves. So we cannot observe the winds well enough to constrain the trend. But look, that's only going from 0 to 0.5. And look, it's mostly yellows. It's actually more like 0.1. So we've got a signal. We can look for trends in this signal. The observations are very nice and clean, and they can constrain the models. And therefore, we can get after what the wind stress changes look like by looking at it through the agent of the waves. That makes sense? So waves not only affect climate through mixing, but they detect climate through helping us to observe fluxes, the same way that looking at the energy budget helps us to look at air-sea fluxes of heat. There are also changes happening in the earth. I put this figure in because Moma is here somewhere. But anyway, so this is from Moma's paper. One of the things that's changing is the Arctic sea ice. And Arctic sea ice, part of the reason why it's changing is because waves come banging into the Arctic sea ice. And they just sent up a satellite, which nobody knew what to do with, except for measure the sea ice. But MoMA figured out that you actually can also measure the waves in between the sea ice and the waves within the sea ice. And changes in the waves within the sea ice tells you how far the marginal ice zone, the brittle part of the sea ice, extends. And so if you keep tracking this satellite over time and keep tracking those wave motions, you can track changes in the Arctic in a really precise way, in a way that you can't easily do with other techniques. So here again, waves are detecting climate change. And then the last part, which is about sea level rise impacts. So one of the things that you're going to notice first, the way that sea level rise will manifest itself in coastal communities is this century is more frequent extreme sea level events. Like the tide's just going to be higher than it used to be. The storm surge is just going to be higher than it used to be. This will be long before the beach goes away. It'll just be inundated more often. And so this is the frequency. So the amplification factor goes from 1, which is no change, to over 1,000 on the dark blue. And so if you look here on the low warming scenarios, you can see there are lots of kind of white, a few blue spots. And these are tide locations. That's why they are where they are, tide gauge locations. If this is 50 years or 30 years from now, and then the end of the century over here, getting more blue over here. But if you go up here to the SSB 585, by the end of the century, all of them are dark blue. So that means that 1 in 100-year flood event is an annual event. If it's this dark blue, it means that a 1 in 100-year event is a monthly event. So that's an awful lot of inundation to think about. And waves are part of the inundation cycle. So if waves are changing, then inundation where the waves are getting weaker, all this blue part of the world might mean that inundation is not so bad because the waves are weakening at the same time as the sea level is rising. Whereas in the Southern Ocean, the waves are getting stronger and the sea level is rising. So you can put that into that part of assessing the impact. Okay. So waves can help us detect climate change, and they're part of the climate change impact. Okay, so the last piece that I want to talk about, let me see, I'm doing it for time. Perfect. Is that waves affect the mixed layer, and so they affect climate. So this goes into the Hasselman model, which is Hasselman, recent Nobel Prize winner in physics model, which is always fun to talk about. Regional mixed layer affects climate sensitivity. Okay, so what is the mixed layer? This is a movie, which is very not smooth, showing the mixed layer bearing. This is a climatology of the mixed layer depth. And so in the winter hemisphere, it's very deep, approaching 1,000 meters in some locations. And it's pretty shallow through the tropics. And this is something that we measure with Argo floats now. So this is not an Argo, exclusively Argo climatology, but this goes up and down. And it's the mediator really of the ocean response to climate change. All those air-sea freshwater fluxes, air-sea heat fluxes, air-sea momentum fluxes are going through the mixed layer first before they get into the deep ocean. It's also home to Langmuir turbulence and submesoscales. We didn't really focus on it too much, but all that stuff, the wavy stuff that we were talking about at the beginning, lives in this mixed layer, and so would respond to changes in those phenomena. And just because I'm here, that was the French version of that climatology. This is the UCSD version of that climatology, which said different things with smoothing and they're missing data gaps, but broadly similar. The wintertime hemisphere is deep, summertime hemisphere is shallow, and it's always shallow kind of in the tropics. Okay, so that's what the mixed layer is. What if we think about it in terms of climate change? There's a signal to noise issue lurking here. So global warming is about an anomaly in top of atmosphere of about 0.7 watts per meter squared, which if we lived on a planet without an ocean and it all heated the atmosphere, we would get deep trouble because that would be 1.5 Kelvin per year change of global warming. But the ocean helps a lot. The upper 3.4 meters, the ocean has the same heat capacity as the entire atmosphere. So if you just put all that energy into the upper 3.4 meters of the ocean, it'd be about 1.5 Kelvin per year, but just that, whatever 4 meters depth. If you think about a typical mixed layer, so here's a typical mixed layer from the side, 30-something meters, it's only be 1.5 Kelvin per decade. And if you think about that profile of which part of the ocean is heating that I showed you before, it's really about 800 meters of the ocean that's heating up. And so you get about 1.1 Kelvin per entire period of time over the industrialization. So the short answer is almost all of the anomalous energy from global warming is ending up heating the upper 800 meters or so of the ocean. That's the simple story. Okay, so let's jump over here for a second. This is an typical annual cycle at Ocean, well, it used to be weather station, it's now Ocean Climate Station Papa, which is out in the middle of over there in the Pacific. It looks like this now. It's got a nice little buoy that's anchored. And so it keeps temperature profiles. And you can see here's summertime, so a nice shallow mixed layer, very hot SST. Here's spring in December, January, deep mixed layer. So it's mixing down, grabbing up this cold water, and then warming up in the summer, and then mixing down, going back and forth like this. And it's changing its depth from about 120 meters to about 20 meters. There's a lot of heat implied in that. In fact, it's about 100 times this signal. So not only do we need to model the mixed layer, but we need to model the mixed layer to better than 1% accuracy if we want to keep track of this signal on top of this back and forth seasonal cycle. So this back and forth seasonal cycle is something we really have to be good at modeling. So all of those details about Langmuir doing this and that and the other comes into play when we think about getting that kind of accuracy, 1% on top of the basic changes in the upper ocean. This basic changes in the upper ocean also impact weather, which is the reason why this thing is out there. This is such an important part of the world that before there was this, the Coast Guard parked the boat there all the time. They kept a boat at that location to make weather measurements so that places like this would have better weather forecasts, because this is the place where the cyclones would start up and then come to land here in the atmospheric rivers, I guess, too. Okay. So, all right, now we've got our idea of mixed layers in our head, Langmuir's in our head, mixed layer Langmuir, seasons. Okay, how much does Langmuir do to the mixed layer? This turned out to be extremely hard to measure accurately. This is a map of the percent increase of a model that includes Langmuir mixing over one that does not. It's about 10 to 20% deeper in the wintertime, maybe 5 to 10% deeper in the summertime. Okay, that's what we're talking. That's how much Langmuir counts for. Different model, same question, a little bit smaller number. Okay, so we don't really understand Langmuir well enough to get this number that precise, but we're still ballpark 10%. Okay, so 10% is the Langmuir effect. Similarly, what about all these beautiful submesoscale dynamics? What does that do? Well, if I didn't have this thing on top of where I am, as usual, also about 10%. This effect can change the mixed layer depth and tends to shallow it in this case by about 10%. Okay, so changes at 10%, changes at 10%. And we're not going to resolve these for a long time. We got to figure out how to get these pieces together. Climate change will already be well underway by 2100. We can't hang around and wait until we resolve them. Okay. So let's get real. Such small changes, about 10% to the mixed layer depth from Langmuir, submesoscales, et cetera, really do anything to climate change? Are we just navel gazing and thinking about dynamics that are cool? Yes, we are. But also, we think we're improving climate models. So let's see if we can figure out how to estimate how much. So I can't tell you what would happen if I fix the mixed layer by these kind of dynamical changes in a climate model, because we're not good enough at it. We can just do these 10% or so changes. We can improve it, but we can't make the errors zero. But there is a recent trick called an emulator that you can use as an intermediary. An emulator is like machine learning, but it knows some physics. So this is a data-driven physical toy model that we use to simulate the effect of a climate model. And if we do that, we can use the emulator and retweak it and correct its mixed layer depth and find out how much of an impact it makes. So this is where the Nobel Prize for Hasselmann came from. He had maybe the first emulator. So this is a very simple equation where you have random atmosphere forcing weighted by the mixed layer, some kind of restoring, some kind of temperature change. Okay, so climate change, I could change this one and this would respond, or I could put in a persistent anomaly in my atmosphere and take, this is a simple stochastic model. So if you had random heat fluxes coming from the atmosphere like this, you get these kind of wobbly, slower responses in the sea surface temperature. This is what it is in a power spectrum. Depending on what the time scale lambda is, you get kind of reddening. And so lambda was 0, you get a purely red cycle if you just drop that term, but if you put it in, you get reddening for a while and then flatten out, reddening for a while and flatten out. So this essentially means that the ocean responds to atmospheric heating, just like it responded to that crazy, noisy signal of heat fluxes, but it responds slower. It responds with a redder spectrum. So that response slower, we can measure. That's what the thermosteric part is all about, but that's also what this little toy model is about. But that's not quite complicated enough of a toy model for what we need to do. So here's another emulator from Nanodesican. And this is looking on the side. So here's the North Pole and here's the Southern Ocean over here. And so now we have light water up top and then dense water down below. And we know that there's the AMOC and things that are like causing a northern sinking like this. There's an overturning in the Southern Ocean causing a return flow, and it's driven by eddies. And so here in the middle, where there's not much communication between the upper and lower, it kind of looks like Hasselmann's model. It's just, here's a mixed layer. We can heat it up. We can put some atmospheric variability up there. We probably have some other things complicated like clouds that aren't in Hasselmann's model that we might want to think about if we're thinking about this for climate. Up here, there isn't really a mixed layer. It's convecting all the way down, but we know that's where the deep wintertime mixed layers are. Those deep wintertime mixed layers are really talking about when the overturning is vigorous. So if we had an anomalously deep year, we'd probably have more water formed, more North Atlantic deep water formed. And over here, the mixed layer is interacting with the eddy return flow in a really complicated way. So it's not at all clear what happens if we have mixed layers changing the Southern Ocean. So emulator number 2. Emulator number 3, which is the one we actually want to use, is a 2-layer model. It doesn't know anything about northern versus southern, but it does have an upper ocean that looks like Hasselmann plus an exchange term, and a deep ocean, which just gobbles up the heat that comes out of the upper ocean into the deep ocean. These have different heat capacities. This one's shallow and this one's deep. Okay, cool. There's also an epsilon here, which talks about clouds. So Gregory came up with this model in 2000, Winton came in 2010 for the epsilon, and then Geoffroy taught us how to figure out how to tune one of these to match a climate model. So this is the data-driven part. So now we take all the climate models in the CMEP6 ensemble, and that's what these little wiggles are. And we follow Geoffroy's method, which is basically look what happens here in the first 50 years, and then look what happens in the rest, and you do kind of a regression. And if you do a regression right, you can figure out the 6 parameters here that cause this simple system to actually pretty accurately predict, plus or minus 10% or so, the amount of warming you get in the climate model. So we have just a really simple 2 ordinary differential equations. That's all we need, 6 parameters. We tune them up, we can predict how much a climate model is going to warm. So we're all hunky-dory. We could just go ahead and say, okay, we could use these to do climate change out thousands of years, or we can change the forcing this F and make it go hotter, colder. We can figure out what's going on. All right, almost. The problem is none of these parameters are observable. They're all just inside this little model. So if they're not observable, we can't tell which one of those models is right or wrong or anything. So we need one more step first. We have to look at something that is observable and try and relate it to the parameters of this model. And so it will be no surprise to you now, what we're going to look at is mixed layer depth. And we look at mixed layer depth in those 3 regions from the Nanodesican model, the Northern Ocean, the Southern Ocean, the tropical part. And we're going to see if there's a correlation between the mixed layer depths across this model ensemble and these parameters. And there is. This is what it looks like. These are kind of typical ones. So here's something that depends on the Northern Ocean. There's kind of a cluster there's a linear with a big error bar slope. So when the Northern Ocean mixed layer depth gets deeper, this parameter, which I can't even see which one it is, the gamma parameter gets bigger. And what also happens when the Northern Ocean right here gets deeper, mixed layer depth, the North Atlantic deep water gets warmer. So you're speeding up AMOC. That's not so surprising. The tropical ocean has a lot to do with the efficacy parameter. which is kind of cloudiness in the tropics. You make the mixed layer deeper, you get more clouds, you get a different exchange, the atmosphere into the deep ocean. It looks kind of like the Hasselman model. It's just heating up right underneath where that mixed layer change is happening. And then down here, this is the Southern Ocean response, and it's with actually one of the other parameters in the model, and it's also got a fairly linear, it has a funny response. You can see the eddy return flow is making Antarctic intermediate water that's filling up the upper ocean, warming it up. But look, this is blue down here where that's red up there. So if you're too deep in both the Northern Ocean and the Southern Ocean, you don't get any change. You get plus, plus, minus, you get nothing. But if you're too deep only in the Northern Hemisphere, you warm up the North Atlantic deep water. If you're too deep only in the Southern Hemisphere, you cool off the North Atlantic deep water and warm up the Antarctic intermediate water. So you really did need those three regions where the mixed layers are behaving differently in all three. You had to pull it apart a little bit. So even though this model doesn't know about latitudes and longitudes, you do need to know about latitudes and longitudes and what you try to observe. Okay, stop. Almost there. This is a big spread. Mixed layer depth going over from, where is that one, maybe 20 meters up to 300 meters. That vertical bar right there is the observed range. So all these models out here are too shallow, all these are too deep. All these models over here are too shallow, all these models are too deep. All these models over here are too shallow, all these models over here are too deep. So let's squish them in. We take one of those, we take each of those parameters, and we just squish and slide all those models up into the observed range and pay attention to what it does to each of the parameters when we do it, because they're sliding along a line that we know the slope of. So we use the present day observed mixed layers, the anomalies in them, we slide it along like this, we constrain the emulator by correcting the mixed layer depth, and then we use those correlations to infer how much each parameter shifts when we do it. And we get this, which is not there yet. Oop. Sorry. This one is just showing that those are the things that are changing when I do that squishing. We get this. So here's global warming under two different scenarios. This is a 1% increase of CO2. This is an abrupt quadrupling of CO2. So don't be nervous that this is 12 degrees C. We're not going to quadruple CO2. But in time, the model ensemble is this light blue one going like this. That's what the climate models say should happen. This, oops, it just died. My laser pointer just died. This one, this inner part is what the constrained emulators would predict. So the important thing, they're not really disagreeing about where the average is, but look, these are narrower than those were. These are narrower than those were. Even out here at 3,000 years, which is pretty much an effective climate sensitivity, these are narrower than those. So, in climate speak, this is when you evaluate what's called the transient climate response. How many degrees of warming do you get by the time in a 1% CO2 increase, you've doubled CO2? And that, under the constraint of fixing the mixed layer depths, would be about 20% reduction. If you get out here, it's about a 45% reduction in the spread of the effective climate sensitivity. So, all right, we had to really hammer the mixed layer to get it into the observed range. Like it's about 5 times the Langmuir effect, or you take Langmuir together with some other stuff, maybe it's just 4 times. It's not. This is a bigger correction than the corrections we understand how to get the dynamics right for, but those corrections have to do with atmospheric anomalies and cloud problems and all kinds of things. Is that enough to make a difference, a real world difference? Well, here's where the economists come. If we could have the uncertainty range for transient climate response, it would have a net present value of about $10.3 trillion. If accomplished in time for emissions to be adjusted in 2020, all right, we missed that. But if we fall into 9.7 trillion, if accomplished by 2030, we're probably not going to make that either. But the point is, we're about 20% of the way to $10 trillion with Langmuir. To me, that's a pretty valuable thing to spend your time thinking with. So thank you very much. I'd be very happy to have questions.
We have just a couple of questions for Baylor. Anyone would like? Yes.
Who's paying you for applying the corrections?
Nobody yet. But I'm waiting for my check for whatever. I'm waiting for my $200 billion check any day now.
Any other questions?
Yeah, how did you estimate the years for which you might have the level of resolution in the models?
Do I have that? Let me see if I have that figure.
Is that sort of just based on like recent progress and then extrapolate?
It's based on recent progress and it's actually exponential. It's a pretty clean exponential. So basically we can afford to double model resolution every 6 years if we don't make the models more complicated, and every 10 years is what we actually do in CMIP models where we're also making them more complicated. So you can project that forward pretty easily and figure out how long it takes. And that's based on the CMIP models in the past, looking forward and, essentially, but I have a couple of papers on that. I can share them with you if you'd be interested. It's slowed down a little bit recently, which is, I don't know why. That may be that we're not getting as good at making microprocessors, or it might be that we don't know how to use GPUs yet. Either one of those, so it's viable. Yeah.
Just to follow up on that question, I think Bob Hallberg told me one time that if we were actually able to build those computers in 2065, the power needed for them would actually become a pretty appreciable climate term if we were letting them.
This is absolutely true. That's a big problem. They are getting more power efficient. GPUs are helpful in that.
Okay, since the blinds are now open and we can see the beautiful ocean from up here, how about we'll take everyone, please join us outside for the reception if you can. And to remind you, the continuation of the symposium will happen tomorrow, which includes surfing at 9:30 tomorrow morning on the south side of the pier. Sorry, Sean. Much better on the south side. And then also TG, we're hosting TG tomorrow. So please wear your Hawaiian shirt, any Hawaiian shirt if you didn't get one of these ones, and we'll see you outside of the reception or later tomorrow. And thank you to Baylor for being our inaugural speaker, and have a wonderful evening, everyone. Thank you.